Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth.
Hello, folks. On today's episode, we discuss the influence of AFRL technologies, Aerospec engines, and what makes Southern California's testing culture so unique.
In 3, 2, 1.
Nils Sedano, welcome to the podcast.
Hi, how you doing?
Doing pretty good. For our listeners, Niels is a technical advisor for our liquid engines branch in our rocket propulsion division of the Air Force Research Laboratory. But really, Niels' claim to fame is really being a part-time historian for the lab. Given that, Niels, we'd like to play a little game where we kind of test your history chops. You ready to play?
Sure, Michelle, shoot.
So basically, we're going to throw out some space-related, rocket-related technologies, and we want to see if we can find one where you can't draw the connection to the laboratory. We're all pretty familiar with the Apollo program. If you all haven't listened to our episode with an astronaut that walked on the moon, I suggest you check that one out. But Niels, what can you tell us about the F1 rocket engine?
Well, the F1 was actually very tied to the AFRL Rocket Lab. We have such a very close history to it. Not only did we test the F1 out at the lab, we tested a lot of it, actually. During the peak of the main development for the F1, we had 5 qualification test stands going for full engine testing with an additional component test stand. So you could say the F1 was developed at Edwards, and we blew up lots of them. One of them took out a stand too. And one of our best claim to fame was actually that a lot of the combustion instability that plagued the F1 and almost didn't allow the Saturn V to succeed was resolved out at the lab. At the time, there was a lot of a worry that the combustion stability of the engine injector would not be resolved. And it was on our test stand 2A out at the lab that the contractor was able to find the right solution, and we were able to test it and see that it worked. And hence, from there, the F1 actually seemed to find its stride.
You know, I'm glad you mentioned the test stand, because I was going to say we got to do some cool filming of test stands out at Edwards, a lot of historic test stands. So you said 2A. Is that still standing? You can still visit that?
Oh, yeah. In fact, it's really hot and heavy. I joke, it's been in operation or in active test campaigns almost before I came to the lab, actually, since the early 2000s, and there hasn't really been a gap since, and doesn't look to be a gap in the near out years. So it's actually gone through many upgrades, and it's continuing to increase its capability and doing more stuff like we did in the F1 and big rocket engine component stuff.
I mean, it really goes to show just how long the work we've been doing from AFRL's perspective to Edwards Air Force Base to really just rocketry, which ties me to the next technology. So this one, I have some suspicions we may be involved, but I'm not sure. So the space shuttle program, did AFRL have anything to do with that?
Oh, yeah. In many ways. I mean, I'll specifically tie to the rocket engine side and rocket motor side. Obviously, that's kind of our bread and butter out at Edwards. I mean, you could actually argue that stuff for the shuttle was done all over AFRL, but just on the rocket side, the space shuttle main engines are work on a cycle called a fuel-rich stage combustion. Incredibly high performance, very compact packaging, extremely high performance. Those engines were an evolution of an AFRL engine called the XLR-129, which was the first demonstrator of that cycle. I've spoken with a lot of the folks way back when, the old Pratt & Whitney folks, Rocketdyne folks that run those programs, and there's really a lot of interesting stories of why NASA picked up that technology. And honestly, you could argue that NASA would not have picked up the technology to use in the space shuttle main engine if AFRL hadn't proven it out to say, hey, this works, because it's such high performance, such high pressures that there was a lot of questions whether it could actually work and be made to work. To the extent that not only did we prove out the technology, work out the R&D, we even loaned out the residual hardware to contractors to facilitate the space shuttle main engine component testing. So, for example, a lot of the turbopump that was worked on XRL-129 was loaned out to NASA and the contractor at the time, Rocketry, to help accelerate the thrust chamber testing. So while they were working the pumps on one side, they were able to work out the thrust chamber by borrowing our hardware. But so it's one of the perfect transitions of it. But not a lot of people know about the XLR-129, but it was a great program. And that's just one on the liquid side. Then on the solid side, you could argue the strap-on boosters that the space shuttle has bear their heritage to a lot of the DoD work on segmented solids. Solids got bigger and bigger. It was getting a little problematic to make a case that was large enough in one single piece. And the Air Force Research Lab worked heavily on trying to figure out how do you create a seal, create a joint, be able to pour these solids in different segments, have the insulation separate and protect the gap, etc., which eventually led to being able to make huge, huge solids like the space shuttle strap-ons.
Well, we didn't stump you on that one. Clearly, AFRL had its role in the space shuttle program. Now, a little bit, to more modern day. What about SpaceX, like the Falcon Heavy and Crew Dragon?
You could say, especially a lot of the stuff in the more recent times, and often I kind of think back in SpaceX and not the new kid on the block anymore. They're 20 years old now, but even before then, we've been working a lot of the work that they've been doing. Like, for example, a lot of the vertical takeoff and vertical landing, we helped out through our engineers and a program called DCX, which is a DoD program, and kind of worked out a lot of the vertical landing, vertical takeoff, vertical landing stuff with rocket engines way back when in the 90s. Then obviously the claim to fame right now with SpaceX in particular is the fact that the Raptor engine is a wonderful piece of engineering that was facilitated by a previous program demonstrating the technology itself at full scale. And that program was called Integrated Powerhead Demonstrator. So Raptor, as you might know, runs on a full flow stage combustion, compared to some of the fuel-rich or oxygen-rich stage combustion other engines. The Raptor is the first flight example of it for the US, and the IPD, the Air Force Research Lab program, was the first tech demonstrator. It wasn't a small scale by any means. It was a full-scale piece of hardware where we actually tested the entire engine assembly, pumps, pre-burners, thrust chamber, etc. And there's actually a joint program with NASA as well. And the effort actually culminated in around 2006, full engine testing and everything. And at that point in time, SpaceX was barely kind of growing and had its own vehicles. And it wasn't until several years later when they were looking around to make a more advanced, reusable, highly operable engine that the same technology came up. And at that point, AFRL had a kind of closed up the program because it was over for a few years, but we still had the hardware, we still had the drawings, we still had the data, and we were able to transfer all that to SpaceX through several mechanisms. And we were actually, I think one of the benefits was that SpaceX was able to, one, know that the technology would function, would work, as well as maybe get a few years ahead of their development to save cost, money, which, to be honest, is the benefit to the government. SpaceX being able to do something quicker and cheaper means that the government is able to obtain that cheaper and quicker. And you could argue whatever the cost of the AFRL program, we probably got it tenfold as far as the acquisition. So that's seeing itself right now. And Raptor is now flying in Starship, and it's kind of exciting.
Yeah, and I think that explains it well, a little bit, like why AFRL or the Air Force, the government invested, the research and development of technology that we do at the lab. We're not in the business of commercialization, but we need the United States and our partners to get there, and we can help along the way.
Absolutely, Michelle. I think that's the core. It's hard sometimes because we often don't get the credit, but that's okay. We do it for other reasons. We do it because in the end, we know that our purpose for being is actually to create a larger capability, so we stay ahead of our adversaries and competitors and so forth. So if the U.S. and the DoD benefit from it, I think AFRL has done its job. We don't need the credit.
Yeah, no, I mean, like to echo what Michelle said there and really drive it home. I mean, to hear that we're able to help cultivate this interest in industry and also the expertise, the technology, and like you said, the means to do this in a much quicker way, working with the experts in the field, it really goes to show how unique AFRL is to answer a lot of these needs, especially in the realm of space. So, being that one lab with two surfaces, it's amazing that we can help the Space Force and the Air Force complete stuff like this. So, glad to hear that, even going from, back to the F1 project all the way till now with plenty of stuff in between. We're doing a lot of cool stuff and work with pretty neat folks.
Yeah, well, and Ken and Niels, like Niels, you say we don't need the credit, and we don't in a lot of ways, but we want to tell your story. We want to tell the Air Force's story, AFRL's story, because we want those bright scientists and engineers to come work with us, or whatever business professional you are, because you're going to work on hard problems and kind of advance technology, advance science, even if it's not our nameplate on something when it's commercialized.
And it's fun too, because I mean, I personally enjoy it. I mean, you work on stuff that you don't know where it's going to end up. You don't know where it will succeed. You don't know if it's just going to crash and burn. But that's an element that's kind of an exploratory element that I think the government is still the only ones really doing it. The industry is really good at taking something that is in essence, it should work. It's just how you execute it, but it's still very advanced, and they put it together and make it work. But the government is very much in that, trying to find that trade space, creating the canvas. Like with Raptor, Raptor is flying today. It's something amazing. But imagine the technology, the full flow stage combustion technology, was first thought of in the early 90s, and the IPD program to demonstrate this at full scale started in the mid 90s and didn't demonstrate until the mid 2000s, and then it wasn't really picked up until 2010s, where SpaceX picked it up. So you look at that timeline and you imagine the engineers that were working on this back in the 90s and so forth. Could they imagine that there was going to be Elon Musk coming in and picking up the technology? I mean, they've never heard of him. They would have never heard of SpaceX. But you still work on the technology because there was a potential for it.
I think imagine's a good word and maybe a good transition for us. Catching up to modern day, what do you do within our rocket propulsion division? What's the cool stuff you're working on?
We're still working on a lot of the propulsion side. A lot of our focus now are in those shorter term transitions. So a big part of my job is actually looking and identifying a lot of the needs for responsive launch, seeing how quickly we can launch systems, seeing what are the operational steps. Where in the past we often focused a lot on the specific components, we're starting to get into kind of what are the challenges for operations to create a new capability, because it doesn't exist today. I mean, we don't launch rockets quickly today. We want to in the future, and I think we're making great strides, and the industry is making great strides in that area. But there's still a lot of research to find the art of the possible and to demonstrate that. So a big part of my job right now is understanding those technologies, making the connections with industry, helping to, in essence, roadmap the path to create the capability and technology to enable that. So working with a lot of engineers, both in AFRL and in industry, to try to do that.
So I liked what you said with define the art of the possible. And what I'm curious is, you mentioned a few of the ways we're trying to get better at rapidly testing, or at least putting out a lot of these engines you mentioned, trying to kind of match what industry's doing to get them out there quicker so people can use these and get us up to the stars faster. So what is your team doing to help make that possible, or what can we do to help make that possible?
But I think a lot of it is, for us, is how we approach the problem. We approach the problem often twofold. One is kind of increase our understanding of the problem by having better models, for example. Be able to use our virtual tools, and we've been doing that for some time now. And then also how we build things. A big part of our portfolio right now is actually, it incorporates additive manufacturing. That technology has allowed us to really start building stuff and building stuff faster. And then the cost of the part is a lot cheaper. And we're able to, in essence, go back almost to the old days where we build and bust. But now that is not as expensive anymore, because we're able to have that high tempo fabrication. So combine the increased iterations and design tools and higher fidelity design tools that we're able to use, our virtual tools, and then couple that with the increased production rate and manufacturing capability for these new manufacturing methods. You couple that together, and you really are able to make some serious order of magnitudes accelerations on creating new propulsion systems, development, curtail the long development. I mean, our goal, hopefully, is to try to address the burden of the decade-long engine development program and be able to curtail that. And if we're able to cut it in half, I mean, that's great. If we're able to bring it down even lower, perfect. But I think time is a big part of what our focus in development time is a big part of what our focus is in.
So to dive into something else your team's working on or researching the space around is the Aerospec Engine, which isn't something new. I'll have to say I don't really know much about an Aerospec engine. So Niels, could you give us a little maybe Aerospec Engine 101 and then dive into why the lab is spending time on this technology?
Sure, Michelle. I mean, the Aerospec engine has been around a long time. In and of itself is not something new per se, but one of the things that we found through the years is that the Aerospec engine provides some tangible performance benefit for launch vehicles. Actually, you could think of it as an inside-out engine, where it uses the atmospheric pressure to change the size of the nozzle. As a rocket ascends through the atmosphere, it's exposed to different kinds of atmospheric pressure, higher at sea level, lower in the high altitudes. So that atmospheric pressure creates the shape of the exhaust plume of the Aerospec, in essence, to maintain an optimal condition for efficiency and performance. So you get a lot of benefits compared to a regular rocket engine that has a single size nozzle that is optimized for a certain altitude, but obviously as a rocket goes into space, it goes through many altitudes. So the Aerospec is able to self-modulate, so to speak, to be able to maintain a higher performance. The Aerospec has been around for some time, like I said, but it's mainly been tested at full scale, but maybe on the ground. It's been analyzed, and it's never flown. Also, the Aerospec is usually a little heavier, more complex, harder to build. So you kind of roll that together, and you can see that over the last 40 years or so, the Aerospecs never haven't really made it to the show. So what we're trying to do is address both the problems that it has and be able to leverage its benefits. Like, for example, the problems that it had was how it was being built. It had many parts. So now we're able to employ additive manufacturing, different ways of integration, different materials, etc., and be able to do a modular architecture where we're, in essence, using smaller components that we're able to, in essence, build, i.e., additive manufacturing, grow, and bring them together with minimal joints, welds, etc. And it's sort of kind of like a Lego rocket engine approach where we take small pieces and bring them together to make up the entire engine. And that really addresses a lot of the manufacturing impediments. And then we can also use the Aerospec's altitude compensation to get the performance benefits. So, we're trying to solve the problem that held it back. And at the same time, we're trying to take advantage of the performance and finally trying to prove it out in flight. The Aerospec has been around for a long time and tested and on the ground and several engines built, but it's still too risky for anybody to really pick it up until somebody demonstrates it. And you have to demonstrate it in the right conditions, which for an Aerospec is in flight, because we can't really replicate a rocket flying through into space and its overall performance until we actually do it.
You mentioned like it's supposed to be more modular, easier to use. Would we want to give people the capability to, like you said, grow these in house and be able to make some of these their own, so they can start using more like of these Aerospec engines without us having to make it for them?
Yeah, I mean, it's really the intent is to be able to just transfer that to industry. I mean, one of the aspects here in this kind of modular Aerospec architecture is that it's adaptable, it's flexible, it's scalable. And again, it tries to address that it takes a decade to make a rocket engine problem. If you have those components proved out in a single Aerospec, you're at least further along in being able to increase, change something, add more components, etc. At least that's a hope. I mean, there's technical challenges with it. But the intent is that if you're able to kind of circumvent those by leveraging, those more mature components, you're able to, instead of having 10 years to make a rocket engine, which is the norm nowadays, you can have, 5, 4, 3 or lower to make a new engine instead of starting from scratch.
Now, do you promise that when you get one of these to fly, you're going to let us know so we can make a big splash about it, right?
Oh, absolutely. We're very excited. We're progressing quite well, and I would be remiss to say, and we'll be doing several of the engine tests, or our contractors will be doing several of these engine tests pretty soon, actually. So we're chugging along, still gearing up for flight. So we're excited.
So that's something that is interesting, that I like the idea of talking about a lot of the testing, the heritage, and the history we have, especially with what your team's been doing at Edwards. I want to talk about the other part of your career real quick, the one about history, the love of it. So we were told that a lot of these like experiments, even stuff like, the Rocketspec engine itself, things that have either been tested here, conjectured, or have run through at some point, you got to work on what was called the heritage room on site. So when you're working on this, can you kind of talk about what the heritage room is, really what it means for that Edwards Air Force Base? And did you have any lessons learned or cool things you found out while helping set this up?
Oh, yeah. Like I said, this is the heritage room was actually my additional duty at the time when I was younger. So the heritage room is actually a long tradition within the Air Force. Normal squadrons have a heritage room where they have their former commanders, missions that they've flown, paraphernalia about the airplanes they fly, and it's a place where the pilots or the crew kind of get together and bond over the history of the squadron. Well, obviously, we are not a flying squadron. We're a research organization, but we're still a military organization. So we have a lot of that military heritage as well, and traditions. So one of them was to make a place where we're able to kind of exemplify our past, both from a military impact standpoint, but also have a place to hold some of these activities and promotion ceremonies, trainings, etc., similar to a traditional flying squadron heritage room. And for us, it was a place to also gather a lot of our test hardware and show it off. For a long time, we're just squirreling away, but there's a lot of history to it. And for me, it's actually shown a lot of the different elements, and I've learned a lot of the different programs and technologies that we worked on in the course of time of kind of doing this. It's been funny how often I still continue to learn something new that we worked on because, oh, what's this piece of hardware? Like, oh, that's when we worked on laser propulsion. Like, oh, okay, I didn't know we did that.
Yeah, it really sounds like it is like almost the 6 degrees of Kevin Bacon, but it's the 6 degrees of AFRL. Like everyone is like related to us at some point or some way. So it's always a degree of separation, if you will. And something that I'm curious about for the Heritage Room, talking about some of these tests and even artifacts you have from them, how do you hone down like which ones to actively showcase? Is there a cycle? Because with how long your testing's been going on, that seems like an almost impossible task.
The main criteria lately has been actually stuff that is of use for folks. I mean, we have recently had stuff that we roll into an exhibit in the Heritage Room because we were loaning it out to industry. They asked for it, so we loaned it out to industry, and then when it comes back, we're able to just put it in the Heritage Room after that. So a lot of the stuff that we've selected to put in the Heritage Room has been because we had to dust it off and send it to industry anyways. So when it comes back, we go ahead and just put it in for display.
That's cool. I mean, that makes sense too, to have stuff that's actually making real actionable change, that they're like, hey, we know you researched this. Mind if we check that out real quick? And you're like, oh, no problem. And then, yeah, it's got a perfect home. So that just shows that even a lot of the old products we're working on still have such value today. Which, again, the fact you can showcase that to folks who may not know that, I mean, that has to feel rewarding.
Yeah, and I mean, there's examples just even this year where we had hardware that we had to go and find and dig out and ship over to NASA because they needed it critically for one of their programs. We had it on display in the Heritage Room, and for years, the program, the hardware is, I think now 20 years old. Thank goodness we had it in the Heritage Room.
So I'm glad we got to dive into a lot of the history, the heritage, talking about aerospikes. I mean, we covered a lot of very interesting stuff today, but I've been seeing a central theme kind of pull through this. And that's that this almost a Southern California culture, as we heard you put this in a prior conversation, that there's something in the air, something about this creativity, this risk of like not risk aversion, but more like willing to take risks to get either a certain issue, a certain technology, or a certain idea through. So what makes Edwards Air Force Base such a unique place to have that kind of culture, those kind of people in the right place?
Yeah, Ken. I mean, it's funny. It's like we're in a very I would say remote location, and I think a lot of it to that point I think is the same as the main base, the flight test center of Edwards Air Force Base. That culture exists there because they're trying to, for example, in the old days, in the days of the right stuff and such, they were taking a lot of risks and proving out a lot of things, find out whether they're possible. And I think that same philosophy or tendency is also on our side, on the rocket side, on the Rocket Lab side. And I think it's just Southern California, I think, has an interesting culture where there's okay, let's try this out. It might work, might not work, who knows? It's a bit of a Hail Mary, let's find out. I don't know if you're wrong or if you're right, but actually kind of putting things down and proving it out. And hey, if they blow up, we learn something from it. And I think that's common. And whether you want to make some allegory to the flight test center, make a correlation to the industry, the types of industry in space, that are out here and that are willing to take those risks. The AFRL Rocket Lab out here also has that tendency, has embodied it.
And honestly, I think you put it best. If we couldn't get away with that kind of stuff, or at least have the idea to push it or try to make that test work, a lot of things may not have developed the way they did. Sometimes you need to shake things up a bit. And it really sounds like you guys in Southern California, that's part of the mantra, if you will. Yeah.
I think it's fun. I've certainly had a few fun times over the years to blow some stuff up and some stuff that actually I'm starting to see actually being picked up and transitioned. So it's actually I've had a good time.
Yeah, so blowing up in many ways. So glad to hear that you've had a chance to not only be part of that, but really make a huge difference. So it was such a pleasure talking to you today. Thank you for joining us. And maybe we'll hash out some more stories on a few Lab Bites or future episodes.
Oh, yeah. Even today, lots of stuff going on. And you might see some of our hardware, flying out in space and beyond pretty soon.
Stay tuned, folks. Until then.
Make sure to follow us on social media at Facebook, Twitter, LinkedIn,